again?
Yeah, that'll do. Good afternoon, thank you all for making it. I'm Alex, this is Oshan, and this is Lewis. Today we'll be talking to you about the topological data analysis of human movement, being a project started last year by Exeter Math School, working with Exeter University. So what did we do? Well, our project was to see if it was beneficial to include multiple dimensions when topologically analyzing human movement. And to check this, we decided to analyze the movement of a hand in 1, 2, and 3 dimensions, this being your X, Y, and Z. And we wanted to see which one would give us a clear analysis of the data. And we also wanted to see if it would be harder to compute. So just what is topological data analysis? Well, quite simply, it's just a way of analyzing very large data sets in which you can represent your data as point diagrams like this one right here. And this is useful because it enables us to analyze pattern within the data that would just otherwise be missed. So why would we do that? Well, our research will help guide Exeter University on how many dimensions they should use when analyzing human movement. And with their research, they hope to be able to diagnose illnesses of patients, mental illnesses, just by analyzing the way they move, which is quite cool.
So before we knew what we wanted to do, we thought we'd have a look at what last year's students did. And they recorded one-dimensional movement, which is just left and right. And then they estimated velocities from that data, which they could produce a series of histograms. And then by computing the Wasserstein metric between those histograms, they could produce some final graphs. And then by analysing those graphs, they could show that each person does indeed have that individual Milter signature. So then we thought that to make it relevant to our project, we'd update the JavaScript code so it could take information from the sensor in 3 dimensions. We'd then take a fresh set of recordings from 17 people so that we have a new set of data to analyse. We could then utilise topological data analysis and things like the Earth mover's distance to come to our conclusions. And then as an added end bit, we thought we'd compare the clarity of our data to last year's conclusions to see if there is actually any benefit to including that higher number of dimensions when recording human movement.
Right, so for our actual experiment, we used a leap motion sensor in order to record hand movement. And what this is basically an array of infrared cameras that can work out hand position above it, and it can output these as a series of coordinates in 3D space. So we took these and using the JavaScript code, we put them into a CSV file, and we had multiple people come in and we recorded their hand movements over multiple days. So we could build up their motor signature, which last year's group verified that different people have. So for our actual analysis, after we had these CSV files full of hand positions, we took the recordings and we found the velocity that the hand was moving in. And we did this for each of the different combinations of dimensions that we were going to look at. So we were looking at which velocity was it moving in, just left and right, just up and down, and each different combination of those. So for one-dimensional, which is similar to what last year's did, we used the Earth mover's distance to compare the similarities of the velocity histograms and kind of work out how similar people's movements were. So what the Earth mover's distance actually is it's a measure of similarity between histograms, which basically means that if there's a low Earth mover's distance, there's very little change between the 2 histograms, so the recordings will be very similar. If you've got a high value, then the movements must be very different because the histograms are very different. So our project was moving it into more dimensions. So for 2D, we used the Frobenius distance to combine the different Earth movers distances for the dimensions we were looking at. So whether this was XY or XZ or YZ. Then, as a final step, we also tried to do it in 3 dimensions, incorporating all of their movement into one calculation, and we just plotted the Earth mover's distance in each dimension for each axis. So, using this, we then could produce graphs similar to the one shown in the bottom right-hand corner. And these show each point as one person's recording labelled with who it was. So we could see any changes that happened to the graph as we move through our different dimensions that we were using. So if we just look at 7 of the recordings that we took, you can clearly see how on the top graph the points are very spread out, but whereas when we move into 2 dimensions, which is this bottom row of graphs, the points become much more clustered. In fact, around here and here, you can barely tell the points apart from each other, because when doing it in 2 dimensions, they become much more similar. So if we take this and expand it into our whole data set, we can see that when we're using the 17 different recordings that we took, they are much more spread out in 1 dimension, and in 2 dimensions, they become much, much more clustered together. So Lewis will talk to you about what this means.
Yeah, so what conclusions can we actually draw from our project? So the first is that the less dimensions that we use when recording data to be used for human movement and analysing that topologically, the better it is. This is for 2 reasons. The first is that the algorithms that we used in the code become much more convoluted in a higher number of dimensions, which drastically increases the computational complexity of the program, which just is much less efficient. And the second is that, as we saw, the final graphs that we draw become greatly reduced in their clarity, which does make our final conclusions much, much harder to draw. We'd like to thank Piotr Slawinski from the university for his assistance with the MATLAB code and his overall guidance on the project. And thanks for listening.